Hi, I want to do an exercise with you that is our first exercise in projective geometry. And the idea behind these is that you can do them on your own. You can use a piece of paper. You'll have to be able to draw a circle and have a straight edge, and of course have a pencil and a flat surface to do it on. Or you could do it on a computer. You could use PowerPoint if you want, or Word even, and that gives you the ability to draw shapes, whether they're straight lines or circles or points. And with that, either approach is fine. Something nice about using a piece of paper and a pencil is that it gets you off the computer. And then your final result will actually be part of your assignment that you're going to submit each time that we do this. So we'll usually do maybe one of these a week, and you could add this to whatever assignment is going to be submitted, and I'll specify that in general, what you'd be sending in to me. And you could just take a photo of it, just so I know you did it. And the other thing is, if you have problems at it, you can always ask me, hey, what went wrong here? And that's actually where the learning takes place, because we're actually creating a system. This is a geometric system, kind of like constructing the tent house that I showed you the video of. And sometimes things go wrong and you don't get out the purpose or function that you were hoping to get out, or that I was hoping for you to get out, because something went wrong in the system. And correcting that is helping you to better learn what the system is, and in general, that there are rules to the system and you have to follow the rules to get the outcome that's desired, if the rules are correct. And the rules are correct in this, but sometimes they're challenging to follow at first, or if one mistake's made, then everything can kind of fall apart. Let me do an example for you, and the actual act of doing it will help you see it even better. So you're going to start with a circle. So if you're doing this on a piece of paper, you can get a lid, you want it to be a really clean circle. You don't want bumps in it or anything like that. So notice this is a clean circle, and that's the advantage of doing this in computer. I can draw a nice clean circle, but you can do it by hand too. Get a jar and trace the outside of the jar, and there's your circle. Then you're going to select 6 points on the circle. They can be random, and that's kind of the fun thing about this. Any 6 points. Matter of fact, if they're random and kind of clustered towards one side, you'll see the function or the emergent phenomenon even better than if they're not. But even if they are evenly spaced, you'll see the result will be consistent. It'll just be a little harder to see as cleanly as you're going to see in this case here that I'm going to do. So if you want to be similar to what I have, how the points are distributed here, that's fine, but they don't have to be, and it'll all still work out if you do it right. Then what you're going to do is you're going to connect the points consecutively in this case. So I happen to pick these two at the bottom that I'm going to connect. They're adjacent to each other. This one here is, if you like, it's next to this one there, so I just connect it. And then I'll go to the next one and connect that like that. Now you want to make sure that these lines are connecting straight through that point. Notice the points that I have in this picture are just representations of points because they have some width and some height. A true point is infinitely small, and that would be ideal. And you want your line to pass right through that point, which is lying on the circle. So if the point's a little off the circle, if the line doesn't completely pass through the point, those are the rules that are not quite being followed, and the resulting emergent phenomenon that we're looking for won't be quite as clean. All right, so you'll see it as, because it's inevitable that you're going to do something that isn't going to be perfect, and you'll see it doesn't come out clean. And if you clean that thing up, you can get it closer. That's the idea here. But I'm just connecting consecutive points with lines. Now remember, a line doesn't just end at the point. It actually goes on forever. A true line doesn't have an end. So even these are just representations of true lines because I can only draw them so long. But you can certainly see that they extend beyond the 2 points that I'm drawing them through. And there's the 4th one, the 5th one, the 6th one. So I got all my lines drawn in here now. So the next step in this process of constructing what I call Pascal's line, none of these are Pascal's line. They're just other lines that will help us find Pascal's line for this configuration. is I want to number the lines. It doesn't matter where you start. Start numbering them anywhere, but just go consecutively. 1, 2, 3, 4, 5, 6. There are 6 lines, and I happen to pick number 1 to be this one right here, and number 2 is the one next to it. So this is line 1 right here. This is line 2 right here. This is line 3 right here. This is line 4 right there. This is line 5 right here. And this is line 6 right there. And then it comes 6 and 1 are adjacent to each other. So hopefully the numbering makes sense. This is really important that you number them correctly. If you don't number them consecutively in this fashion, then you won't get the result we're looking for. They have to be numbered this way. To make it even easier, in the next slide, we're going to be pairing these lines. So in other words, I'm going to pair line 1, which is this one here, with line 4, which is that one. And line 2 is going to be paired with line 5. And line 3 is going to be paired with line 6. And by paired, I'm going to look at the place where those lines intersect. Remember, any 2 lines intersect, even if the lines are parallel. So I'm looking for those points where those lines intersect. So let's see if we can find them. And in order to make it easier, I'm going to color the lines so that lines 1 and 5, 1 and 4 in this case are blue, 2 and 5 are red, and 3 and 6 are green. And notice now, much easier to see. I just happen to arbitrarily choose these colors so that you could see that very clearly the points of intersection that I'm interested in. So this blue one here is that where those 2 lines intersect is that point right there. Where the 2 green lines intersect is that point there. And where the 2 red lines intersect is that point there. Now, even before I complete everything, when I'm almost done, you might see something interesting here. These 3 points seem like they're lying on a line. And indeed they are. And this is a famous line, and it's known as Pascal's line. And I drew it in black. Now, what's interesting about this is this will be the case no matter what. No matter where I put the points on the circle, you will get a Pascal's line where the lines 1 and 4, 2 and 5, 3 and 6 all intersect at points that join up to create a line. And remember from the last class, whenever you have 3 points that line up, you have a line, and that's a special line. Any 2 points will create a line. But when you have 3 points that create a line, that's something special. And that's what's happening here. To get 3 points lining up is, you'd say, more than a coincidence. There's a reason for that. You can actually prove that this will always be the case. That's not the point. The point is that you can see that this is the case. Pascal's line. It's a systemic property of this projective geometry. And I encourage you to try this and to do it. It's an assignment. It'll be part of your next assignment. This video, you can just follow the video, do it on your own. See if you can get a Pascal's line for whatever 6 random points you find. Now, there are cases where you may not see it as clearly as this, where you get a couple things that become parallel. And I'll talk about that in a subsequent video. If you get that, that's okay. And I'm happy to entertain questions with you. We could get on a Zoom. I can look at what you did and try to find a problem if maybe there is a problem. And there always is a problem when you're trying to do these. They always crop up, and they're learning experiences. So take this, have fun with it, and this is just the beginning. It keeps going from here. And by the way, Pascal's line, I think, was discovered, my memory, I have to check that on this. I think it was 1789 where this Pascal's line was discovered by Blaise Pascal. And we will be talking more about that. We can Google it. And you'll see on Google that you'll see the result of it. But this is how you construct it. Okay, more soon.